right. So this is what is called the rank nullity theorem. One should write dash, it looks like minus, is a rank plus nullity equal to n, right? Rank nullity theorem, rank nullity theorem, right. So this is the last one, dimension of the kernel plus dimension of the range is equal to V. So that is what is called the rank nullity theorem, right. We will see that this is same as the rank nullity theorem for matrices a bit later. Okay, good. So let us look at a bit further. So important thing what we have done is, for a linear transformation, kernel is a subspace of the domain, range is a subspace of the codomain, their dimensions added up give you the dimension of the domain. Okay, right, right. Important consequence of this, very important consequence, says let T be a linear map, then these three statements are equivalent. See, if you have got function from one set to another, in general set theory, a function, then if this function need not be 1, 1, right? This function need not be onto, and there is no relation between a function being 1, 1 and function being onto, right? You can have functions which are 1, 1 but not onto, functions which are not onto but are 1, 1, and both also. But for linear transformation, it is very important and very nice that a linear transformation, if it is 1, 1, then that is same as saying kernel is equal to 0, and that is same as saying T is equal to T is onto. So a linear transformation, if it is 1, 1, it must also be onto, right? It cannot have only one of the properties. Let us see a proof of that. Okay, that so T is a linear transformation V to W. So let us assume one that T is 1, 1. Okay, to show T is on, what is to be shown? T is to show that kernel of T is only 0. That means 0 in a linear transformation, 0 is always goes to 0. So kernel will always be having 0 inside it. Claim is this is equal to 0. So let us show that. So let us take U belongs to kernel. So let us say U belongs to kernel of T and U not equal to 0. Let us say there is something else also possible, right? Then what is T of U? That is 0. That is also equal to T of 0, right? So I have got two elements U not equal to 0, its image is 0, which is also equal to T of 0. So what does it imply? T is not 1, 1, right? I got two different elements, one non-zero, other 0, their image is 0. So that means what? That means this is not possible, right? So hence kernel of T is only 0, right? So let us, so this proves 2. So 1 implies 2, right? So 1 implies 2. If T is 1, 1, then kernel of that is equal to 0. Let us say 2 implies 3. So let us say 2 implies 3. So let kernel of T be equal to 0 to show T is onto, right? That is what is to be shown. So note, range of T is a subset of W, right? Range of T is a subset of W. To show it is onto, I have to show range of T is equal to. So to show actually range of T is equal to W. That is what is to be shown, to show it is onto, right? If the range is the full codomain, then it is onto. Now let us compare what is dimension of range of T. What is the dimension of the range of T? From the rank nullity theorem. Right. So rank nullity theorem says it is dimension of dimension of range of T should be equal to rank nullity theorem. So, what is the rank? Rank is the dimension of the range, right. So, that is equal to dimension of the range should be equal to dimension of V minus kernel of T, right. But what is that dimension? Kernel is 0. So, what is the dimension? Dimension is 0. So, it is dimension of V, right. So, dimension is full, that means what? It has to be equal, right. It has to be equal. So, that is the third one, it is on to. Okay. So, all the third one follows because of the consequences of okay. Is it clear to everybody that these three are equal, right? The third one is a consequence of rank nullity theorem. Okay. Now comes the crucial thing, namely how are these linear? We said that given a matrix you can generate a linear transformation out of it, right. We can generate a linear transformation out of it. Now conversely we want to show that given any linear transformation, it arises that way only, arises through a matrix multiplication only. That is the only way of getting a linear transformation. Okay. So for that, let us have this notation. If V is a vector space and you have got a basis V1, V2, Vn, ordered basis, once again the order is fixed, right. So what does that mean? It is a basis. Every vector V, you have got linear unique constants alpha 1, alpha 2, alpha n, unique scalars, right, such that this vector is a linear combination of them, right. That is a basis. That means you have got unique scalars alpha 1, alpha 2, alpha n, and their order is fixed. Alpha 1 is for V1, alpha 2 is for V2. So let us write this as a column vector, alpha 1, alpha 2, alpha n, these unique scalars which are coming in the representation. So you get a vector, right, you get a vector in Rn. This is called the coordinate vector of this is called the coordinate vector for the vector V. V is, right, an element in the vector space. These are coordinates which is written as a matrix form, the unique linear combination. So this will be called as the coordinate. So what is the theorem? The theorem says the following, that if T is a linear transformation from V to W, right, on V, let us say dimension is n, dimension of W is equal to m, then we have got a basis, dimension is n, so there must be a basis. So fix a basis, V1, V2, Vn, ordered basis. For W there is a dimension m, so fix an ordered basis, W1, W2, Wm, okay. Then it says that if you fix these things, then there is a m cross n matrix. T is from where? V to W. What is the dimension of W? M. Dimension of V is n. So you get a matrix of order m cross n. It says there exists a matrix such that if you look at the image vector T of V, look at its coordinate vector with respect to the basis in W. It is same as take the matrix A, multiply with the coordinate vector of V in the domain, right. So it says that TV can be obtained by matrix multiplication, right. So every matrix is being associated, every linear transformation is being associated with a matrix, right, of order range cross domain m cross n, such that this matrix, this linear transformation can be realized as matrix multiplication, right. How is this matrix obtained? That is the question. How do you get a matrix for a given linear transformation? Okay. So let us look at a proof of that. I will write the proof first and then show you, so that is a revision. So T is from V to W. right? Here you have got a basis B1, which is V1, V2, Vn. Here you have got a basis V2, which is W1, Wm, right? T is from V to W. So let's write for every vector V belonging to V, V is a linear combination of V1, V2, Vn. So that is equal to alpha 1 V1 plus alpha n Vn, and these are unique because of basis. So what is the coordinate vector? That is alpha 1 alpha n, right? That is what the theorem statement of the theorem said. Okay. So now consider what is T of V. T of V is this. So what is T of V? Alpha 1 V1 plus alpha n Vn, right? Using linearity, it is alpha 1 T of V1 plus alpha n T of Vn, right? So let us just shorten it instead of writing dot dot dot. So this is sigma alpha I T of Vi. So let us keep this as it is. That means if I know T of Vi's, I know T of V. That is what I said earlier also. What is T of Vi? So note T of Vi belongs to W, is the image, and for W we have got a basis W1, W2, Wm. So implies that T of Vi must be equal to sigma scalar multiples of Wj. So let us call them as something, say alpha j I of Wj, j equal to 1 to m. Is it okay? V1, V2, Vm is the basis of W or W, right? So Wj, j equal to 1 to m is a linear combination, and these are the scalars which are appearing, I between 1 and, for every I you will be getting a scalar, right? T of Vi. So these scalars which appear in the representation, they will depend on I, right? There will be j, for each I there will be j of them, say that T of Vi is a linear combination of multiplied by Wj, j1 to m. Is that okay? Right? What I am going to do is, from here I am going to put the value in 1 of T of Vi. I am going to put back the value. So what will happen? So let us see and put back the value. So implies T of V is equal to, we had sigma I equal to 1 to n alpha I T of Vi, that is sigma j equal to 1 to m alpha j I Wj. Is it okay? I have taken this value T of Vi, which is this. I have put this value here in this expression 1. So alpha I equal to 1 to n, and T of Vi, that value is put here. Okay. So just this value T of Vi from here. So this is my T of Vi. Is it okay? Check. T of V was equal to sigma alpha I T of Vi, right? And T of Vi being an element of W must be a linear combination of Wj's. So that is the expression for that. So this value I am putting back in that equation, T of V. So it says T of V must be equal to sigma alpha I T of Vi, this value I put. So this is the expression I get. But where is T of V? That is in the range, right? I should express it as a linear combination of Wj's, but they are inside. So I interchange the order of summation. There are finite number of sums only, right? So I interchange. So what I get? j equal to 1 to m, I equal to 1 to n, right, alpha j I of wj. Okay, I just interchange. I was here outside, I have brought it inside, j was inside, I have brought it outside. So alpha j I, right, alpha I summation over I. So this thing is independent of I now because I have been summed up, right, some scalar it will come. So let us write this as beta j. This depends on j. So what is it? T of v is sigma beta j wj. That means what? That means this T of v, which is in w, its coordinate vector with respect to w must be equal to alpha, this summation. Let us write beta j, beta 1, beta j, beta n, right. So what is beta j? Beta j definition is I equal to 1 to n alpha j I alpha I for every j, right. Do you recognize what is this? What is beta j? If I take a matrix with alpha j I entries, then how do you get the corresponding entry here? Multiply by alpha 1, this multiplied by that one, right. That is precisely equal to this. This is metric multiplication. So implies that this vector, okay, so let me just write here that beta 1 beta n beta m is equal to the matrix alpha j I and alpha 1 up to alpha n. That is precisely, this equation is precisely saying this. Right. See, alpha j I, what is j? First one indicates the row, second one indicates the column. So in that row, look at and multiply by alpha 1, you will get this vector. So this is the matrix A which corresponds to the linear transformation, right. So I think we will spend some more time because he indicated that his time is running out. But let me just, so what it says is the following. So the proof, so the important thing is the T of V is a linear combination that we get here, right. These are the, so this is what we get, the coordinates of TV is A times, okay, where A is the M cross matrix alpha Ji. Important thing you should notice, I purposefully wrote something which, see here when I write T of Vi as a linear combination, I wrote J first and I later. Purposefully I wrote because then only it gives me the corresponding multiplication. Okay. So that means what? From our point of view, it says the following, that if T of Vi is this linear combination, for ith element in the domain basis, if you write as a linear combination, you will get scalars, right? Those scalars are nothing but the ith column of that matrix. That is the crux. In the domain, you have got V1, V2, Vn. In the codomain, you have got W1, W2, W1. So look at the ith element of the domain basis, T of Vi, that is ith element in the domain, right? That must be a linear combination of W's. Those scalars which are coming here, right? How many are there? M. That form the ith column. So this I gives you the column, and W1, W2, the scalars we give you the elements of that column. So to find a matrix of a linear transformation, fix a basis of the domain. For each vector, look at what is the linear expression, write down the column. So let me just look at one example. So let us look at this to finish off. T of, this is a linear transformation, okay, from R3 to R2, x, y, z goes to comma this expression. Check it is linear, that is easy to check, right. So, what will be the matrix of this? Order will be 2 cross 3, right. I want to get the columns of that matrix. So, in the domain R3, let us fix the 1 0 0 0 0 1 0 standard basis in the domain. 3 elements are there. For the first one, T100, according to this formula compute, right. According to this formula compute what is T of 010. So, I got these 3. So, what are these 3 things? 1 2 is the first row, because it is the image of the first element of the basis. This is the image of the second element of the basis in the domain. This is the third element in the domain, its image is minus 1 3. So, that is the matrix. In the domain V1, V2, Vn, look at the ith entry, write this as a linear combination of that side, and that gives you the ith column. That is how you get the matrix. Okay. So, we will do some more examples next time. Thank you.